Okay. Good evening. My name is Joseph Garcia, and here's my presentation on drone simulation and control. Let's see. Okay, starting off the first one. So let's all go ahead and think about this. So what this whole series is about is basically showing us how a quadcopter can be simulated and controlled. The quadcopter can be controlled in 6 degrees of freedom, but only has 4 actuators or 4 propellers, 4 motors. So it falls under a category of rotocraft, which is what the quadcopter is because it uses a rotating wing instead of a fixed wing to generate lift, generate up and down, or any of the motions. On some quadcopters, there are multiple sensors that do different things, such as an ultrasound sensor on the bottom of the quadcopter, which can be seen here, that little circle looking thing. And on the bottom of the quadcopter, that shoots a high frequency sound pulse downward and measures how long it takes for the sound to come back to determine the altitude of the quadcopter. The ultrasound sensor only works with short distances, such as 15 feet or less, since the increase in distance will ultimately lead to the reflected sound from the Earth to be too soft for the sensor to receive it again. So, moving on, let's go to the next one. Okay. And so drones often have many cameras, which is also seen right here, that little small dot. Has many cameras on the bottom of the rotocraft, not to present videos and pictures for the audience, but to take pictures and compare objects in the frames. Doing so, the drone system can calculate horizontal motion and speed by tracking a single object in both frames and measuring how far they've moved over time. Let's go to the next one. So another sensor that's commonly found on the drone inside the drone is pressure sensor, which simply measures the pressure in the air to calculate altitude. And the higher the drone goes, there is less pressure in the air. Lastly, there is a sensor called an inertial measurement unit, or IMU, which is a 3-axis accelerometer that handles measuring linear acceleration, and an axis gyroscope that measures angular rate. This unit can use these measurements to determine how fast the quadcopter is rotating and the angle in degrees relative to gravity. So a quadcopter has 4 actuators, which we talked about, and so they form this X orientation. And for many reasons, this orientation has proven to be the best so that we can maneuver and utilize all of these different types of maneuvers: thrust, roll, pitch, yaw. And we can go all of our different directions: left, right, up and down, backwards, forwards. So the motors directly diagonal from each other spin in the same direction, while the others set spin in the opposite direction. And next one. Okay. And so the control problem of a quadcopter is to take 4 inputs as torques and forces from the motors and output maneuverability in the 3D space. This is achieved with feedback that is measured with sensors. Finally, the error is calculated through here and taken as an input to a controller that will correct and command each other to achieve an overall goal of a maneuver set point. And then we'll go to the next one. And so basically these are some of the the different maneuvers I was talking about previously. But since the quadcopter has only 4 actuators and 6 degrees of freedom, the maneuvers can be translated as such. So we have 3 transitional directions: up, down, left, right, forward, backward, and then 3 rotational directions: roll, pitch, and yaw down here. And so our task is to make the controller execute all 6 of these degrees. So below here are some simplified executions of each maneuver, broken down in terms of force to each actuator. Go to the next one. And so in reference to the control systems, the plant is the quadcopter that takes 4 inputs as the commands for the 4 actuators. If we were a part of the control system, we would be part of the feedback of the control with a controller, such as down here. We can adjust in any way necessary if we go a direction we did not plan to go. If we start, veering left, veering right, we can control that correction back to our desired state. And so we, in turn, become that negative feedback, or become a form of that negative feedback. Okay, let's go to the next one. And so if we want to make a drone hover at a certain point, we need to implement an altitude controller that can keep the quadcopter from deviating up or down. So, but it's not just that simple. To solve this discrepancy, we need to understand that there are other forces that will happen, such as wind gusts, that will knock the quadcopter off balance from the axis of gravity. And so in order to solve this, we need to control the thrust to the motors so that we can avoid the quadcopter from tilting left or right. And then in other words, extending too far up, falling too far down. And so implementing this will require many factors that one may not think of during this act. Roll, pitch, yaw, and altitude all have their own degrees with reference to the axis of gravity. When a gust of wind comes, we need the quadcopter to constantly read the position on the ground so we can correct back to that starting point when the quadcopter is knocked off course. Also, we need the quadcopter to lean into the wind to prevent so much force generated against the drone and knocking it too far left or too far right. So, using the set of sensors, we can generate error calculations for each maneuver for each maneuver, so we can correct left, right, up and down, forward, backward, while maintaining the proper altitude. And so, here's a little diagram that was referenced in the video. And so really, this block up here, the position reference, that's what controls your left and right position according to the globe's perspective of left, right, the compass and whatnot, to get us back to the starting point of which we were at. And so, doing all of this, it's pretty awesome that we have MATLAB and Simulink to aid in model-based designing and tuning applications to tune, because we have to tune each and every one of these controllers here. So that can be a daunting task. However, MATLAB and Simulink, they do a great job with having packages available that we can, start with a base of. And so to build the flight code, that's what's going to be next, right? So the code that will be implemented by controllers of the drone, we need to make a rough diagram of how it should be performed. Starting with Simulink, we can generate a code in C. Starting with Simulink, we can generate code in C program that is based on our diagram, and then convert that to binary code, and then transmit that code to the drone via Bluetooth. Let's go to the next one. So fortunately, the Simulink already has a base support package for Parrot mini drones and allows us to design our own control system that can be paired with the software's present portions of code. So as you can see, we have some Bluetooth, LED, motor, um, messaging, memory management, battery management. So these are all things that go into the quadcopter that that are kind of taken care of already for us. And so we really have to focus on this flight control software. Okay. And so as always, when controlling the quadcopter is one thing, but we also need to understand that there are additional items that need to be added to the system, such as a state estimator, which handles calculations between different states for the sensors. We also have fault protection, which implement thresholds and limits in the case the quadcopter needs to be shut down immediately to avoid harm to either the hardware, our drone, or others in case it starts going towards some pedestrians that are just casually watching. And then we have data logging to record data to be used in commands and calculations. And then I go down here. And so when simulating the drone and modeling software, we can save time, hardware, and physical quadcopter failures by simulating the drone software in any situation we can think of, such as too much wind, cold temperatures, anything that you can really think of. And so when simulating, we can leave out certain things like LEDs, since there isn't much effect on the entire system when say like a gust of wind comes. No one really cares about the LED, and that's fine. It's so simple that we don't need to take it into account once we already implement it. So simulation is great for linear models. So we need to linearize our model or our controllers. And with this linearization, let's go to the next one. So with this linearization, it may not be an exact match to that of our true system, but it should get us pretty close to what we're thinking of, or exactly how it should act, right? And so here, listed here, we have many subsystems that can handle some of these anomalies that occur in the environment. Right here will be environment down here. So, it says constant, but some things can change as always, and we all understand that. But we have other things such as like airframe, nonlinear airframe, and I believe that is like how the quadcopter is constructed. Some things to also take into account that, is your quadcopter flexible? Does it kind of flex with, let's say, airflow around it, or is it more of like a rigid body that will not give at all? And so these are some of the subsystems that are present, and then also in the middle is our flight control system. That's pretty much what we are working with and tuning to perfectly fit our mini drone. And so let's go to the next one. And so as seen here, the simulation software looks great compared to reality. Well, of course, not great, but it looks pretty good when in the software you can simulate failures and all types of failures. The drone tipping over, the drone crashing into something, or even more fine details like, oh well, when this drone takes off, you can kind of see it starts veering to the left without doing anything, just veering to the left by itself. And so obviously those are some things that you take into account, and you would go back into your model here and see, okay, so upon takeoff, it's already getting pushed to the left, say with a little 3 mile an hour wind, which can be simulated. And so then you would need to kind of correct for that. Okay, well, maybe I need to start focusing more on my right shift maybe making it a little too weak. And so, of course, that can also affect other things in the whole model itself. And so, tuning the controllers is easy with MATLAB and Simulink Aerospace-based models. So we can start tuning the independent controllers that affect nothing else, such as the altitude and the yaw blocks, right? So they're not in sequence with any other controller, unlike these, which they are in sequence. And so you would need to account for multiple controller changes, and they'll directly affect each other, right? And so, so while altering one aspect of the system, we should keep all other controllers constant so we can solely focus on one or another controller. And so that's really going to be apparent in the pitch and roll sequences, because affecting this PNID will also affect this one, and affecting this one will also affect that one, and vice versa. And so these ones, they're solo, they're just by themselves, so it's more of a simplified diagram. And so, consistently running new tests and focusing on other factors will eventually lead to a fully functioning quadcopter that can operate in 6 degrees of freedom. And lastly, here is the reference to the YouTube channel. And so big shout out to them for teaching me how to do all this. I mean, it's purely invaluable to have this kind of information available at just at our fingertips. And so I would like to thank you all for my demonstration.